So we had 25 cubic centimeters of a mixture of iron and iron 2 and iron 3, correct? And we know that the potassium permanganate is going to react just with the iron 2. And so to just figure out how much iron 2 I had, I took the amount of potassium permanganate times its concentration to figure out how many moles of permanganate reacted, and then use that 5-to-1 ratio to figure out how many moles of iron 2 there would have been. The ratio of the moles of iron 2 to the volume of the solution gave me the concentration of just iron 2. In the second part, we're told that we can use zinc, and the zinc is going to reduce the iron 3 into iron 2. When we did that, instead of using 15 cubic centimeters, we used 19 cubic centimeters of the permanganate. So now I can figure out how many moles of permanganate I used for both the iron 2 and the converted to iron 2. That means I know the moles of both of these things. So I know the moles of just iron 2 and the moles of both iron 2 and iron 3. So by difference, I can figure out how much of this was iron 3, divide it by the volume, and get the concentration. So that is how I approached 8. I'll leave it there for a minute. I was just scanning these so I could put them on the canvas, so this won't be a secret. But that is my approach to 8. She's just going to take a picture, so she's light years ahead of me. Questions on 8? Where'd you go wrong on 8? Sounds like I did not go wrong. This is one of the ones I knew how to do.
I didn't necessarily go wrong, I just gave up.
Okay.
For instance, the question is so hard to understand. I got to the 0.006 part, but I didn't know.
Okay.
To go.
So I chose these because I think that there are frequently.
No, I know, I get it.
Yes.
I know. It's like a real thing that really even because like I know, I still know like which one is like it was like number 10, like I didn't know that, only at the acid reacts with sodium
Why not?
and non-potassium. I didn't know.
But how would potassium hydroxide, how would potassium ethane dioate react with a base? Because if anything, ethane dioate is a conjugate base. Right.
I just wanted that it feels like a
I chose it because I think we feel this shitty feeling on paper 3, and I feel like if you feel this crappy feeling now on a homework assignment in January and get used to it,
And it won't feel as bad.
it won't feel as bad on the real thing because you're like, I've been here before. So that was my thinking.
This is the kind of stuff we'll see this for.
I think you often see experiments that are things you could have done. And I would say this falls into that camp of something I could do. Like I really understand the iron and permanganate part of this story, and then they like did this weird zinc thing, but they kind of explained why.
And this is myself.
That's fair. I don't have a feeling. There's nothing here that is obviously HL, but is hard. So maybe that's what makes it HL. And I think that, like, if we go back in time and think about Sophia before her first test on stoichiometry, like, this is exactly how she felt on every question. Right? Like, I understand the formulas, but I have no idea how to actually do them here. And I would like her to have some of those feelings now so that she can get over them, continue to get over them, succeed, feel confident when she's answering these questions, instead of being surprised by them on an exam. I am looking for things that are going to be off-putting, intentionally. So Audrey gave away all my secrets for number 10, so can I go to 10? Are we done with 8? We're not done with 8, Margaret's still right. Margaret, right away. I'm gonna drink some tea.
Okay.
One of my many failings today was forgetting my cup. I struggled more with this one. I don't know if I can get it all on one page. I can. So we're gonna do it in 2 batches, I apologize. But in this problem, we had a mixture of ethane dioic acid and potassium ethane dioate. And Brecken's gonna tell you, hey, that sounds like a buffer. Yeah, I'm gonna giggle. So we're gonna take this and first we're gonna titrate it with sodium hydroxide. And then we're gonna do a redox titration with it. And we're gonna try to figure out something about the potassium ethane dioate. So as we practiced at the very beginning of our titration class last time, this is just a straight up acid-base reaction. So you figure out the moles of potassium hydroxide. You use the fact that this is a diprotic acid to find that 2-to-1 ratio between the hydroxide and the diprotic acid to figure out the moles of ethane dioic acid, which in turn would give you the mass of ethane dioic acid. Since you know the mass of the solid, you can figure out the mass of the potassium ethane dioate. Just gonna leave that there, and you can ask any questions you want, but I used the first titration to independently determine how much potassium ethane dioate was in the sample. Did you kick ass on this, or did it kick your ass? Or are you just waiting until midnight tonight?
No, 10's the only one that I had.
Question.
Some faces we can read, some faces we can't. Yes?
In the actual question, right, it'll say like, for example, 78 pubes was titrated against blah, 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 and it says no firing 17.35. What do they refer to?
So it took 17.35 cubic centimeters of sodium hydroxide of a known concentration to react with 25 cubic centimeters of your magical mixture. So again, we use that titration, so this is what Amarachi was just speaking out. We knew how many cubic centimeters of the potassium hydroxide and its concentration, so we got the moles. We used the 2-to-1 ratio to get the moles of the acid, and we used the molar mass of the acid to get the mass of the acid. We got to play the game that we knew how much was in 25 cubic centimeters, we were interested in how much was in 250 cubic centimeters, so I multiplied through by 10. Seem to have some lack of clarity if I want that or not. I would like a 3 there. You know, you want to keep your things looking solid.
Is there a particular reason why we're calling it potassium hydroxide instead of sodium, or it doesn't matter because they're both structured? About the sodium hydroxide?
Because the teacher doesn't read well. Sorry.
Where did you get the ratios from? Like the 2 to 1?
The 2-to-1, so, because this has 2 H's, it's diprotic, I knew that it would take 2 K, not further embarrass myself, 2 NaOH's to make 2 waters and 2 sodium ethane dioates. So I was just writing the neutralization reaction, and since it was a monobasic base, just 1 OH, and a diprotic acid, H2, I knew that there was gonna be a 2-to-1 ratio. And I felt like that's the reaction more or less we started class with last time, and maybe that's why I'm so sure this should be potassium. But it's not, I fixed it 3 times.
So then how do you know what problems that you need to figure out the balancing equation? You just do it for everyone?
Every problem, like, so one of the lessons I learned from this was I need a balanced chemical equation to solve this problem. And so the reason that this was pertinent to what you were learning is because we had to balance all the redox jazz. And what you have done before in this vein is balancing the acid base jazz. I think if you go back to topic 1, I see Sophia, I'll be there in a second. There were lots of questions about waters of hydration, about titrations of this to determine waters of hydration, about using multiple pieces of information in a problem. But no, I do not think this is realistic.
What does that say after 4.97 times 10 to the negative 4? Is that like an M?
It's gonna say moles.
Oh, moles. Okay, cool. Thank you.
Welcome. Okay, so if you guys believe that I can figure out how many grams of potassium ethane dioate were there, we can move on to the second part of this problem, which is gonna be to figure out how many moles of that stuff are there. And so to do that, we did a second thing. It was a redox titration. And we were told about the amount of potassium permanganate that we used. Remember, amount is the IB word for moles. So given the concentration and the volume, we could take their product to figure out the moles of permanganate. Now, I was lazy with this, but I know because we've been talking about it a lot, that this is a 5-electron reduction. So I imagined this equation. Did you guys imagine that equation? Did I do anything dumb? You can just tell me out loud. And they gave me this equation. And I knew that I needed to combine the oxidation and the reduction. In order to combine them, I knew that I needed to find the lowest common multiple of 5 and 2, which is 10, which meant I had to multiply that top reaction by 2 and that bottom reaction by 5. That meant that the ratio of permanganate to ethane dioate was 2 to 5. So once we knew the moles of permanganate, got that 2 to 5 ratio, we could figure out the moles of ethane dioate. But we knew that there were 2 sources of ethane dioate in the reaction. I knew the total, and I knew how many I had seen before, so this difference was the moles of the potassium ethane dioate. If I knew the grams of potassium ethane dioate, and I knew the moles of potassium ethane dioate, this ratio would give me the molar mass of that jazz. If I subtract the potassiums, the carbons, and the oxygens, I would get just what was water, and I got 17. So I said that there was a singular water. There should be a 17 here, I'm feeling. I'll scoot it up just a tiny bit. Said something terrible in class yesterday. I'm like, thank goodness no one's filming. Melania films.
What did you say? You wanna share?
I mean, I didn't say like I hate you. I said like the number of electrons doesn't matter for this, and it clearly does. And so I like tried to fix the sentence, and I kept trying to make it right so that it would look good in their notes. But like I still had said it, and I'm like, thank gosh, there's no evidence that I said these words because I just kept trying to dig out of the hole of having heard myself say it. It wasn't that good of a story, but yeah, she was like, yeah, I have it, and I'm like, so just for the record. Do you want to see 2, 4, 6? Some of the tired.
Wait, hold on.
Okay, you're gonna write faster.
It's,
I don't need to say two,
Okay.
because other people do it.
Does anyone else want to see 4? Is that yes, DC.
Yeah.
I feel like the work's all gonna look like my work. I don't feel like I organized it very well.
Is that a part of us?
How miserable are you, Brecken? How can we make it better? It's not a couple of weeks.
Just have to. Find it all.
Sorry. Quattro. Photocopied this amazingly for you. And number 4, we have a tablet. We're putting it into some acidic solution and making it up to 250 mils in water. We're gonna take 25 of those milliliters and react them with potassium dichromate. And we're gonna try to figure out the percentage by mass of iron. So this is the lab that your neighbors did in 5th period. I got this 6-to-1 ratio because it was on the front side of the page. It's like, yes, we all did. So I took the concentration times the volume and got the moles. I used the 6-to-1 ratio to figure out the moles of just iron. The moles of just iron were in 25 cubic centimeters because that's all I titrated. But the question is about what's in the whole 250, so I multiplied by 10 to keep the ratio constant. I took this number of moles and multiplied by the molar mass, 55.85, to get the mass of iron. So I have made the assumption that iron 2 and iron have the same mass. I think that's fine. And then the mass percent is going to be this mass divided by the total mass of the tablet. Is the mass of water, yes ma'am. I'm gonna pass out something if you guys wanna keep looking at that, that's cool. Yes. Number, yes. I just found the molar mass of that, so I took 2 times 1 plus 2 times 12 plus 4 times 16 is 90, plus 2 times 18 is 36. So I hope that I multiplied the moles by a number real close to 126. Multiplied by the molar mass with the waters.
Wait, so.
Yes, the hydrated thing, because I know the formula for that. That's why I did it. Multiplied by the molar mass of the hydrated thing. Does it look right?
I mean, I can't tell, but, number 6,
Yes.
there's like a point where we have to use like where I found like this for the
Yeah.
moles of iron. and
Yeah.
so it's 50. But then like after that I was stuck, so we are it's like online, but like it says why do we apply this to like the entire salt? Like,
Because
why
if
does
you look
this-
at the formula for the salt, how many moles of iron are in the salt?
What?
So if you know how many moles of iron you have, you know how many moles of salt you have. So we're just using the ratio that's in the salts.
Okay.
Okay.
Because I was gonna actually ask that, because I don't understand why Fe2 plus would represent it.
So you can see that this whole salt has 1 unit of iron in it, right? So if you have 1 mole of iron, how many moles of salt must you have?
That same amount.
1, right. So if you figured out how much iron there was, the moles have to be equal to salt. Now if you had figured out how much sulfate there was, then you would be like, oh, there are 2 sulfates here. So I'm gonna have to take a 1-to-2 ratio.
Okay.
But it's just because there's a single iron in the salt that we can do that. Do you want to see 6? Okay. All right, let's do 11. Okay, let's take a quick look at 6. So one more time, they told me how much permanganate it took to titrate it, so I found the moles of permanganate. I used the 5-to-1 ratio that was on the front side of the paper to figure out the moles of iron. And I knew that I needed to know the moles of iron in the whole solution, not just in my 25 centimeter cubed aliquot. The question that I was getting from my left table, I don't know how to call you guys, is why do we know that 1 mole of iron is gonna tell us anything about this compound? And it's because we see that there's just 1 iron in it. So if we know how many moles of iron we have, it's exactly equal to the moles of this whole compound. And that is very much a multiple choice question. That's like a real question. If they had told us a way to figure out sulfate, then we would have said that there are 2 sulfates in this, and we would have divided the value by 2. Same thing for the ammonium ion. There are 2, but it's just because we have 1 iron and this has 1 iron that there is a 1-to-1 ratio here, so we knew how many moles of this weird salt we had. So I multiplied by the molar mass that I didn't give you, and this would be the mass of the salt. The difference between the mass that we had and the mass of just the salt is the mass of the water. We can figure out how many moles of water we had, and then the ratio of the moles of water to the moles of salts is what N, the waters of hydration, are. I don't feel like I liked the way I did waters of hydration better for 10.
You moved on, I thought the water mass that you just calculated on your.
Yes, and I just didn't write it down. I was lazy. It's gonna be my answer. I apologize. So as I just promised Karthika, this will go on Canvas. And when you find mistakes, you can let me know, but I'm relatively confident I'll write it. It's a longer room He's not a poster for getting your ACL reconstructed, I'll tell you why. In football, he tore his ACL when he had the surgery. We have to go to school. He could be on medical leave. I mean, he was off last week trying to recover. And I think felt better. But I think the reality of school is that it's relatively uncomfortable, right? There's not pillows and blankets and whatever you need the way you might be able to have around the house. I feel like this was an uplifting experience. I had so much fun with this homework, remembering good old days. I want to talk to you today about the activity series and about voltaic cells. Does that sound right to you? What?
And about what?
Voltaic cells, batteries, galvanic cells, Daniel cells. I have like 30 different synonyms for them. And so I gave you a POGL. We are not going to go through all of the joy that is the POGL, but I have written the key. I believe that I finished it during first period today. And so I will post my answers to the POGL. I find them a very effective way of learning things. I have found that people are of very divisive opinions, and some people really like them and some people really hate them. So if you are someone who likes them, like, go to town. It's how I learned all of the biology I know, which ain't a whole lot, let's admit. They work for me, but that doesn't mean they work for you. Some people find them mindless.
What's a POGL?
What you are looking at right now, like, this document is a process-oriented guided inquiry learning exercise. You're supposed, process-oriented guided
I
inquiry
thought they just
learning.
made up a word for like practice
So I don't like the process-oriented part. That means that I'm supposed to say that Amarachi is the speaker for her group of 4, and she's the only person who's allowed to ask questions. And Mohab's gonna be the timekeeper, and so he has to make sure, I can't enforce that. I've just never been there, but I do. Don't you have any of this?
There's a time limit.
I do really like the guided inquiry part. I like the fact that it asks questions instead of telling me answers. That I find effective.
What is the field stand for?
Guided inquiry learning.
Back guild.
So again, I enjoy them, but I'm not like enforcing it. I'm not making it homework. I just thought that some of you might also think the teaching in this section is somewhat lackluster and needs some extra support. This is my least favorite unit, Margaret. Leaps and bounds, least favorite unit. So hate redox. Hate it. I think because so much of the time it's what you shove in at the end of a year going as fast as you can. So like in AP, this is the last unit. And SL did it before organic. That's right. In IB, it's not meant to be the last unit, but I'm saying like growing up, taking chemistry classes is always the last thing, and you're always just freaking flying. And like, I'm good at some of it, but I know there's lots I'm missing. I don't have any color. Like, I can just do it. So maybe this is gonna be your favorite unit, because damn it, I can just do it.
I understand when you do it, I see where you're going, like I see what you're doing, and I understand it when you do it, but I have no idea where to start ever on anything. And that's just,
That's why I like the questions instead of the reading, because you know the book always knows the next step, and you're always like, oh, this isn't so bad. Then you're doing it, you're like, shit. Sorry, that's my whole life. Like I find reading extremely, like, oh, I mean that's easy. Let's go. And then you're like, oh, I have to actually think for myself and do it. That's very hard suddenly. Okay, so the first thing I liked, the first reason I printed this is because there's like a demo experiment on the front page. So you see it's labeled activity series, and you see that there are a series of like time-lapse photos of some beakers. So each beaker has a solution in it, and it has what we might call an electrode in it. And we're asking ourselves the question, does anything happen? So in that first, we have magnesium. It's sitting in zinc. And the question is, does something happen? And all of you are saying, yes, it does. And so you can see that in a few ways. You can see that zinc metal is being formed. And you can see that magnesium ions are being released. So you might be able to tell me that magnesium is being oxidized. You might be able to tell me that zinc is being reduced. You might not. Well, the computer scientists are laughing at me.
no, she read really wrong.
Okay. Like, it seems obvious to me, and not meant to not be, what would happen if I took zinc and I put it in magnesium? That's the question. Would the same thing occur, by which Rami means the opposite? I mean, she is Audrey. So the way chemistry usually works is that if one reaction is spontaneous, like this one, this occurs, the reverse reaction that Rami was kind of indicating does not occur, right? What?
Like they're still like next to each other.
They're next to each other, but this reaction doesn't occur. This is the more stable, lower energy, like free energy is gone. This will just sit there forever. And so we can actually make a statement about which of these metals is easier or harder to oxidize. based on either of these data points, based on the fact that nothing happens or based on the fact that something happens, I hope we can look at this and say that magnesium is easier to oxidize than zinc. And we refer to that as saying magnesium is more active than zinc. So the activity series for metals is a series that shows the easiest to oxidize at the top and the hardest to oxidize at the bottom. A way to determine that order is to do a series of single replacement reactions like the ones shown here.
When it comes to like metal, like the more reactive it is, we might be more willing to
The more reactive or active a metal is, the easier it is to oxidize, the easier it is to remove an electron. So you guys know from chapter 3 that cesium is going to be real active because it's really big and it doesn't have a whole lot of cares about that last valence electron. So you have some sense in topic 3 about some trends, but when we get into the middle of the table, or when we're comparing a transition metal to a main group metal, we don't have that kind of insight. And so we have a data booklet. And so the data booklet has a table on table 25, and it is called the activity series. Now, because I am, a little bit racist, and I think that some of you have learned poetry to tell you about activity series. I was like, Tree, certainly you may have learned this. Like the number of Vietnamese kids who have come in with like a poem to tell me the activity series is so high. Like it's clearly something taught in school somewhere. So I found, please stop calling me a careless zebra, instead learn how copper saves gold. Have you heard something like this before?
I said this.
You said this?
She said. She created.
So I should have quoted you, like this is Dash Audrey?
Audrey invented it. I did not invent it. Like I can't remember she was beginning of last year.
It's a bit coherently. I think you mentioned that at the beginning of last year. Because I remember you
Yes.
saying zebra like made a little alarm.
I remember you saying zebra.
Yeah, and it was like careless zebra and gold.
Yeah, so I wrote it down and I've had this in my backpack for the last 2 weeks so I could have this moment with you. I didn't have it with second period. I don't know it clearly because I have to like save this shite notebook. But Moheb and I are simple-minded folks and we know that we have a really nice diagram that shows this to us. So one of the questions you might ask is, what am I honestly responsible for? You're responsible for the trends in chapter 3, which you'll look at real fast and see they don't make any sense because lithium is more active than cesium, and that's going to make you cry inside, and we're just going to ignore that fact. So this is going to be that part of the story where I say, I can do this, but there are lots of nuances. I can't explain to you why lithium's not where it belongs.
We're responsible for trends.
So one thing you're responsible for is trends from chapter 3. So you should expect that cesium is the most metally metal. That's how I would have said it back in chapter 3, that it's really good at giving up electrons, is how Audrey said it today because she's a better adult than I am. The next thing that you are responsible for is a general pattern. So I am looking at this table 25 in my data booklet, and at the top I have a whole lot of alkali and alkaline earth metals. At the bottom I have platinum, palladium, copper, gold, silver, in no specific order. Where would I find platinum, gold, or silver in my life? Yeah, it's on the periodic table. That is where I find them in my life, Amarachi. Let's be honest. But typically we think about it as jewelry and coins. You need to be able to look at what you think of as expensive metals, jewelry metals, whatever it is, and say, we can't oxidize those. They don't tarnish at the same rate. They are not active metals. So if it is a multiple choice question, Sophia is asking herself, would I wear it? Not active. I don't think that she has real ideas about lead versus iron. I don't expect anyone on paper 1 to ask her about lead versus iron. But I think they do ask questions about zinc versus gold. Okay, so the trends from topic 3, just size. As size increases, we think that metal should be easier to oxidize. And then Would I wear it as jewelry? Would I make a coin out of it? Does it cost more than whatever? I don't know what the bar is. So, that's easy. Oh. But I'm interested if we can look at this data some more and come up with a series, so matching this table, of the metals that are involved in the experiment that is called Model 1 in front of you. So I gave you the first piece, that based on this experiment, I can tell you that magnesium is more active than zinc. What would the second experiment tell you? B. Magnesium is more active than aluminum. Strangely enough, magnesium is also more active than copper. So we know that magnesium is more active than all of the metals that we have here. And so he's the winner. He is the most active of the metals. I like to think about activity of metals like I like to think about activity of kids applying to college. You are trying to convince your admissions decision makers that you are an active member of a high school. What does that mean to you? That you do stuff. You are not sitting there in your metally inert state. Gold does not do stuff. The metals that are active become parts of things. They're going to make salts. You're going to have magnesium chloride or zinc chloride. They're going to go lose their electrons and do stuff.
What was the guy that gets into Harvard because of his parents going there?
Now, let's not poo-poo nepotism. Okay? As a parent, I got into some schools, and I expect my kid to get into them too. I understand all you high and mighty people feel like by my merits alone. I mean, you guys are gonna face different things in your life, but as a member of the people who, like a girl in STEM at my time, it was like, well, clearly you got in because you're female, right? I mean, everyone looks at you like, oh, girl, yeah, of course you're here. Like, let's have some special programs for the girls. We'll call it the Bridge Program. We'll invite them to college early for a couple of weeks because they certainly don't have the same, things going on that the boys had. And you guys come from all over the world, do all sorts of different things. People are going to make assumptions looking at you like the reason you got here is because of X. Don't put up with that bullshit. Don't put up with it. You got there because you should be there. No one is ever going to be able to circle one part of you and be like, Sophia made it because of this. Like the pigtails are cute, but that's probably not the reason. Okay, how about zinc and aluminum, zinc and copper? Do we know anything about those?
No, it's less active than aluminum.
Oh, zinc lost to aluminum. So I'll write it in the right way so you guys don't have to think about greater than signs. How about copper and aluminum?
It's copper one. It's aluminum.
Aluminum one. And how about zinc and copper? Do we have any idea?
Zinc one,
It does, but I don't even, oh, we see it in experiment I. The copper didn't win.
I think. Oh, yeah, yeah. Why are the liquids different colors? Like, some are darker than others.
Copper's blue, so they
Because
just
copper's
made it
blue and they're trying to show you that, and I don't like you enough to print color.
There's a color?
And then here, it's like a few cents like more expensive for the brand different colors.
It's not even the fact that they tell me how much more expensive it is. It's that I have to wait until this message comes up and hit I really mean it, and that message can take minutes to come up, and I just don't have the patience for it. And you just feel like the printer didn't print. I really mean, you do. So if you want to single side things, or if you want to make them in color, there's a pop-up that's telling you that you're wasting money, and you have to say, I really need this to be single sided. Please, let me. Some of you had Miss Riley. Miss Riley was the photocopier to pass all photocopiers, and so she got this thing like you spend $40,000 photocopying, and all the money is monopoly money. Like they just have a what?
Geometry teacher?
She's the one that gets candy.
With the little bucket.
She was a breakout teacher.
Yeah, she's a
curly
state
hair,
actor.
right?
I
Yeah.
had a class with her over the summer.
Lucky.
The algebra and
I
some
freak out. I don't think she liked me very much.
The geometry.
How would she not like you?
I wasn't very good at
She
it.
likes everybody.
She'll, one thing about it, she'll give you candy.
She even brought
assign some penny amount to pages
Everything is.
that isn't what it really costs.
Yeah.
For the summer part.
For some reason.
Thank you.
As long as you pass with like a 80.
I got a 42 on some, whatever exam.
That's a common multiple choice question that clearly I might struggle with, but Ramey's gonna get right. They'll give you some reactions and you need to put some metals in order. They will not give you the zebra metals because they don't want you to memorize some cute little poem. I'll write it on Canvas or something if I feel the spirit moving.
Something else on my goal.
Gold zebra.
Alex? I thought you were just
Oh, no. Please stop
So let's just take a moment and discuss the magic of this. Like, it's clear that I don't enjoy this, but it's clear that it's still a really big part of chemistry. And the reason is that we can harness this to do our bidding. How do you think we're gonna harness this? Electricity and batteries and stuff. So what Elizabeth is telling me is that the electrons on magnesium are a little bit angry. They're in a relatively high potential energy state. And the electrons would be a whole lot happier on a lower energy place like zinc. And so these electrons will flow from magnesium to zinc. But in flowing from here to here, it's a bit like water. We can put a water wheel in between them. And if we put that water wheel in between them, the electrons or water will still go, but we can get some energy out. I do this all in terms of water wheels. Isn't that fascinating? So that's what we're going to do. We're going to make this into a battery. We're going to find a way to take chemical potential energy, the electrons that are a little bit angry to be on magnesium, and turn it into electrical energy. My laptop is currently running on a battery. Is this physics? Yes, perhaps that's why I didn't like it too much.
If you.
But we have Quinn. And so we're gonna take this reaction that is spontaneous and we're gonna try to get the energy out. So a long time ago, we talked about spontaneity. And spontaneity we measured with delta G, that gives free energy. This would be topic 15. So you had a few formulas for delta G. I just heard something about delta H and delta S, so you might recall past successes like delta G is equal to delta H minus T delta S, or I'm quite fond of delta G is equal to minus RT ln KQ. So that one's a good one. Those are in the data booklet, so if you're like, oh my god, I don't remember formulas, like the formulas are frizzle, just knowing what they mean is on you. Sophia's full deer in headlights. Like her eyes are so big and she's like, oh my
I have
god.
never heard that second one. There's no way. I saw it, but there's no R. No, because I was the. What is R in that?
R is the ideal gas law constant.
We had to.
That one
use
used
it
with the graph on the back.
And the graph on the back?
Yeah.
I remember.
And then,
Yeah.
And then like I was to use the, wasn't it for the slope or something?
Rate, you actually rate slope.
Yeah.
That's why I don't get it. I never got a
Isn't it
single
called
one of those
R?
questions
Oh, no.
right.
Yeah, this is a rock star problem. Like I really love this.
It was, if I was to do it, I did it right, I guess. But it's a little.
I like it. So I'm talking about free energy. Josiah Willard Gibbs, the 1800s, is like, let us name something after me and call it free energy.
That was like a fifth grade.
So for the past N years, where N is relatively large, we've only had 2 papers during monks. This year, she has given us all 3 papers.
Maybe she's testing.
No, so in the past several years, we've been told that we can only enter 2 assessments into the grade book because we've only had 2 tests. So I assume that we're gonna keep the weight the same. It's 2 test weight, and I don't know how we're gonna account for the extra paper.
So, you know, you could just use it as like a buffer, so whatever you got wrong with others.
It's just extra credit, paper 3 shall be extra credit.
You take the 2 best graded papers that we do and just put those in.
I'd be honest.
hard to do a paper 3 this year. Is that for
She's feeling specifically sadistic this year.
For math, you have the paper 3.
Yeah, but is it test grade? No, I'm not concerned about how many papers there are, I'm concerned about how much weightage it has in the grade.
Weightage.
Weightage,
Weightage.
Wait.
Weight.
Yes.
I would go with weight. I think you made up the word, and that gave me some joy. So this is something that is mandated by my Carrie Peters. It is not something that is mandated by me.
So is it always 2 test grades?
It has been 2 test grades for a long time. I have a meeting today, and I will have a succinct and binding answer to you perhaps today. So you want to know the weighting of mocks.
Yeah.
No, weightage is a word.
Weightage is a word, what does it mean?
Allowance or adjustment weighted or
Should we ask if it was the right word?
Okay, it means the value or importance of something when compared with another thing.
Wow.
Yeah, so she used it.
That's why she's got a 7 in HL English, and we're just like.
She got the excellence award.
That's funny.
She got the excellence award in every subject you take. Like,
Oh my gosh, that was so big. Go Jessica.
So if you ever want to teach me some English, the one I really don't understand is the difference between comment and commentate.
Like
the
the,
commentator, which is commenter.
And orient and orientate, people use that. That 8, I don't know what it means. It changes the part of speech somehow,
Is it a
but
British
I think it's just fancy.
I thought commentate was a verb, comment is the like noun, is in the comment thing.
but no, I'm gonna comment on your IA, but I'm not gonna commentate on it. Like I'm not gonna have a press conference about it. I mean, it could. I don't know. I mean, you are the speech and debate queen, so again, like I will defer to your greatness, but I believe they are both verbs.
It's like as it's happening, and then comment is like past tense, you're seeing it, and commentator. Yeah, but like commentator is like they're commenting on something as it happens.
No, not commentator, commentate.
But wouldn't that be?
As a verb, not as like a person's
I know, but like commenter, commentator.
What would happen if I put a zinc bar in zinc? Nothing at all, because zinc is exactly as active as zinc. Nothing can win here, nothing can lose. This is like a boring solution. But over here, I'm gonna take a copper bar and put it in copper.
This one does something that's blue.
This one's blue, but also does nothing. And what I'm gonna do to make this interesting and new is I'm gonna attach them by a wire. And so now, if we listen to what Elizabeth said a long time ago, she said that high energy electrons on the active metal, zinc, again, I don't make money or jewelry out of zinc too much, are gonna go and they're gonna be like, ooh, what we could do is we could find a low energy place to go. We know that naturally, if we were to put zinc metal into copper solution, it would make zinc and copper metal. So wouldn't the electrons be willing to flow through the wire to make this happen? And the answer is yes. Yes, they would be willing to do that. Yes, please. And so what we're gonna watch over time is the zinc electrode will be eaten away. The copper electrode will build up. The copper solution will become less concentrated, less blue, so we would observe the blueness. The zinc solution would become more concentrated, we wouldn't see anything, so we don't talk about that too much. But we have now separated this into 2 cells and forced the electrons to go through this wire, but as they're going through, just like my water going down a hill, we could get the energy out. So I could actually shove a light bulb right here. And those high energy electrons should be able to give me some electrical energy, light my light bulb, and then those more relaxed electrons should be able to go find their happy home on the copper.
Why does the copper solution become less concentrated when the zinc becomes more?
So if this reaction is really taking place, because we saw it on our first page of stuff, the copper stuff in solution, the copper 2+ salt, is becoming copper metal. So the fact that this electrode grew is because the copper in solution plated out or was reduced. And similarly, over here, the zinc is going to be turned into zinc ions. It's going to be oxidized. And so as the zinc is oxidized, we're going to find that this electrode is eaten away. And so the zinc ions are going to float into the solution, so the concentration would be a bit higher.
So, it being like taken away is just like it going into the solution?
Yes, so the zinc metal is going to become zinc ions in solution. So I won't be able to see them.
And then the copper, the solution is decreasing because it's going into the gold bar?
Yes.
Oh.
Wait, so isn't the zinc like, aren't they like kind of going to the other side, like the zinc going over there?
So the electrons are going.
The electrons are going.
The electrons are the only thing that's able to flow through this wire.
Okay. And on like the copper is, why is the copper like,
Fattening.
yeah,
So the copper 2 that's in solution is taking the electrons. The copper 2 that's in solution is taking the electrons from the zinc,
to become copper?
and it's becoming copper metal.
While on this side.
While
yeah,
this side is losing the 2 electrons and becoming zinc solution. So on the left-hand side, the process that's occurring is oxidation. And on the right-hand side, the process that's occurring is reduction. If I'm paying attention, I will always put oxidation on the left. The electrons are always very well behaved, and they travel from left to right just like I read. This is a convention that is used across textbooks. Doesn't mean the IB will do it every time, but if you're drawing a cell, traditionally the oxidation goes on the left, and the electrons are moving to the right. Yes?
Quick question, when you told us that you need to know the trends in taking chocolate for your ladies activities, what's chocolate?
Periodicity?
So just like alkaline.
Yeah, more shells means that the electron's easier to remove because the Coulombic attraction is weaker.
So there's certain like you know the other ones have like arrows when it's increasing this way and does that have one or is it just like
So francium is like the best, and
okay.
it's the same arrow. To denote that the electrons want to move to the right, we traditionally put a plus sign here and a minus sign here. If you look at a battery, you're going to see it has a plus and a minus on it. The plus means that's where reduction is taking place, and the minus means that's where oxidation is taking place. There's a kind of gross problem with this cell. Some of you were thinking it internally, but you're too nice to tell me. The gross problem is that as the electrons leave here, what is the charge increasingly over here? Positive, and it's increasingly negative over there. So at some point, it's just going to be too expensive for an electron to leave something that's already positive and go over there to something that's already negative. And so the piece that we always draw in last is known as the salt bridge. And we usually fill it with a very concentrated solution of potassium chloride, potassium nitrate, sodium chloride, sodium nitrate, a salt. Those are the compounds. And so every time an electron leaves here and it wants to be positive, a chloride ion will flow this way to replace it. And every time an electron arrives over here trying to make it negative, a potassium ion will come over here to replace it. So this is allowing us to maintain charge neutrality. And then without this, the cell will only run for like an instant, and And then it's gonna be like, ooh, too much negative charge. But if we put the salt bridge in there, it'll run just like a battery for quite a long time because we have made sure that both cells are gonna become neutral. So this dude named Michael Faraday is like, we need a name for these two cells or for these two electrodes. And he decided to base it on what's going on in the salt bridge. So here I have the cation potassium and it's traveling to the right. And so he decided to refer to this electrode as the cathode. It is because cat ions flow there. And he decided that we shall call this cell where the where the anions flow, the anode.
But I know only electrons.
So electrons flow through the wire and ions flow through the salt bridge.
You just leave it there while the salt disappears and
Yes. But it's probably more likely that the zinc could disappear. But yes, like this is how batteries break. Batteries break because the electrode's no longer able to conduct electricity, or because we can't maintain charge neutrality. Like we use a bigger battery to force things to flow the other way. So the alternator in your car is gonna reverse the direction that your battery is turning. Some people notice that these are both vowels. Some people notice that those are both consonants. Some people say anox and a red cat to remind themselves that anode is oxidation and that cathode is reduction. An ox and a red cat went to a party to celebrate electrochemistry. An ox and a red cat went on an adventure. I don't know what they did, but you can write that story. I don't much care. They did.
And never made and found gold in
The things that you need to be able to draw when it says, yo, draw a voltaic cell, and we'll call this a voltaic cell. The specific structure that I've drawn here, and the only one that you need to know, is known as a Daniel cell. Daniel does have 2 L's, some guy's name. As Raimi can tell you, you can spell your name however you want.
Is that entire thing?
Yes, like the 2 beakers with the salt bridge in between them is known as a Daniel cell. This is the cartoon that we'll always draw. What you need to be able to show is the flow of ions, so the cations and the anions going the right way, the flow of electrons from the anode to the cathode, the minus sign on the anode, the plus sign on the cathode.
not to label the zinc and the copper.
I mean, labeling the electrodes is lovely. They may even do that for you, like the questions that they're gonna have are the flow of the ions, the flow of the electrons, and the polarities of the signs. You can see that it's a little bit cumbersome sometimes to draw that picture. Like imagine yourself with a typewriter. So imagine me growing up and looking at science books and they're like typing. And so they came up with something they call line notation. Line notation is in that long list of the things that the IB will sometimes use but will never ask about. So the question will never be, Moheb, can you write this in line notation? But when they're describing a problem, I've seen it increasingly. And so the way line notation looks is you take the anode, which in our case is zinc, and you write it. And then you say the anode is a solid and the solution it's in is a liquid. So I'm gonna draw a bar there saying, yo, there is a phase change here, solid and liquid, different phases. And so the zinc is in a solution of zinc cations. Zinc nitrate, zinc chloride, zinc I don't know what. And then this cell, this whole thing being the cell where oxidation is happening, is connected to this whole cell via the salt bridge, which is denoted by 2 beautifully vertical lines. And then we would find ourselves here in the copper solution, which is in a different phase than the cathode, the copper metal. So that is called line notation. It's showing you the redox couples. So it's showing you that the 2 things I have going on are zinc is doing something and copper is doing something. It's putting the oxidation on the left. Like it's just trying to simplify a lot of this into one really short space. Again, I am never gonna ask you to write it, the IB is not gonna ask you to write it, but they'll just put this in a problem trying to describe what's going on with probably some more information, but I don't want that to be the first time you see it. So this is now the first time you saw it, it's probably not super important, but in our quest for no surprises, let this be no surprise. So this reaction is occurring spontaneously. That's what makes it a voltaic cell, the fact that the electrons spontaneously are flowing toward that positively signed cathode. What do you think might make the electrons, flow harder? A more active metal. So I could tune how these electrons are flowing by selecting metals that are somehow more or less active than each other. So if we right now have this redox couple, maybe we could get more high energy electrons or like a bigger battery if we use these or these. And so instead of having it as a qualitative list as you do in table 25, which might still be open for you, but may not be, who knows? You can go back in time in the data booklet to table 24. And table 24 is now the HL part of this, where instead of trying to give you the relative activity of things, I'm going to give you a numerical value to associate with how good or bad things are at being reduced. So everything in this table is being shown as reduction. So at the top I have lithium. Remember, lithium's my most active metal, and I am trying to take lithium cations and reduce them to lithium metal. Is this something I think should happen? Lithium is the most active metal per table 25. Should it be possible to take lithium and reduce it? Should be really, really hard, right? Lithium wants more than anything to lose that electron for this table, so putting an electron on it's going to be really difficult. So we associate that with a large negative value of something we refer to as the standard reduction potential. So the standard reduction potential being negative means I don't want to do this. Let's look at the bottom and see what we have there. At the bottom we have fluorine taking on an electron to be fluoride. Which element in the periodic table has the highest electron affinity? Within reason, it's fluorine. It's actually chlorine. You snotty little kids, you know too much. But yes, let's pretend it's fluorine for a minute and say that down here we're seeing a reaction that is extremely likely to happen. So the reason that I wrote delta G earlier in the notes is to tell you that there's actually a relationship that I find useful, that I feel like Amarachi's going to find useful, but some of you aren't into delta G, and that's okay. It tells me that the spontaneity of a process is proportional to this cell potential, this number that's listed here. But the proportionality involves a minus sign. So if I look at the first reaction here, lithium has a big negative E. Karthik is going to tell me that delta G is positive and that reaction is not spontaneous. At the bottom, we're going to see that the fluorine reaction has a large positive E. Brecken's going to tell me that delta G is negative, that reaction is spontaneous. So I'm not in a place where I'm ready to really use this formula, but I know it's in my data booklet, and I know what spontaneous means in a way that I'm not yet sure what cell potential means. So just to connect it back to something you've seen, that helps me to understand what's going on. In my head, this thing, the cell potential, or the reduction potential in this case, I'll tell you the difference. It's telling you something like the height of the water for the water wheel. If you have water that is well underground, you're never going to be able to use it for the water wheel. If you have something that's way up here, you have a chance. If you're moving water from up here to way down here, it's going to have a lot of energy. I'm going to have a big battery. It's going to be a lot of work available. So to me, this is something about the height of the water. Quinn, you want to talk physics? What do you think of as a potential?
What you said, like gravitational potential, the higher something is, more it has.
Yeah, so I'm thinking about gravitational potential energy, because it is a nice analogy to me for this electrical potential energy that I have like a weaker understanding of. I can write formulas to show you how it's related to energy, and I'll write that real fast. 1 joule, that's energy, everybody, is equal to 1 coulomb times 1 volt. A coulomb is an amount of charge, and a volt is what I'm measuring this cell potential in. So if I know how much charge I'm allowing to move, I could get something about the energy. Much like if I knew how much water was moving, I could get something about the amount of energy that was flowing. So if I just have a trickle of water, it doesn't really matter how high the high is and how low the low is. If I'm trying to actually grind my mill, I need some water a-flowing, and that's what I'm gonna get here. So the connection between the height of the water, the height differential of the water, and the amount of energy that I get out is gonna be the number of moles, so this is gonna be like the amount of electrons flowing. And F is known as Faraday's constant. He's the same guy that gave us the names for the anode and the cathode. And it is the charge, 96,845 maybe, of a mole of electrons. So every electron has a charge of 1.6 times 10 to the minus 19 coulombs. There are 6 times 10 to the 23rd electrons in a mole of electrons. If you multiply those two numbers together, you get this number that tells you what is the total charge on a mole of electrons. So if I take a charge in coulombs times a voltage, I get an energy. So again, these are the units that I think that Quinn knows because he's in that physics class, but the rest of us probably don't work with coulombs and volts very often. Fair? Miserable? Extra miserable?
Could you talk about that, like the water thing again? Yeah, that potential.
Okay, so we're gonna talk about that water thing for the rest of class until it's time for you to look at your homework. So what Karthika told me was that if I made the difference between things larger, then maybe I could get some more energy out. So I'm gonna use my fingers to try to show Moheb something about the water. So here I am looking on my sheet here for the copper reaction. Does everyone see copper here at a positive 0.34? And now I'm gonna look for zinc. Zinc's gonna be up here at a negative 0.76. So one of the ways I use this water analogy is I use my fingers. And I think about the distance between these two things on this table. I can see it's about 1.10 volts for those of you who are good at math, but I can see it's about this far away for those of you who are good at fingers. So Karthika's suggestion was that if I wanted to make my battery bigger, what I could do is I could use a better metal than zinc. And by better, I mean a more active metal than zinc. And so what I'm gonna do is I'm gonna replace my zinc with magnesium, and does everyone notice that my finger moved farther away? That water's flowing farther, it's a better battery. Now, the rest of you who want to be dignified when you have conversations with others are going to notice that the difference in between these things is now 2.71 volts instead of 1.10 volts, and 2.71 is a larger number. You feel that? So we've learned a trick, maybe. It gets worse when we do electrolysis. There's lots of fingers. Not that finger that you're thinking of.
What? Like,
It's just a bad joke. I know you got it.
It's that finger.
what finger?
If I wanted to measure the, if I wanted to measure the cell potential, that is going to be the difference in altitude of where my water starts and where my water ends, or the difference in sort of gravitational potential energy, as Quinn so eloquently put it. What I'm going to do is I'm going to use this table, and I'm going to look up the reduction potential at the cathode, and I am going to subtract from it the reduction potential at the anode. This is an HL skill, putting the numbers in. Some of you are gonna be bothered that you know that zinc is being oxidized in this reaction, and I am using 2 reduction potentials. Some of you are gonna think that's some boo-boo. That's why there's a minus sign here, to indicate, yo, I'm actually oxidizing this. The problem with explaining this too much is that at some point Emma starts flipping the sign like 3 times and she doesn't know if she's coming or going. So my strong recommendation to you is to just use the reduction potentials as given. Every time I give you a value associated with redox chemistry, it will be a reduction potential. And I know and you know that one of those things is going to be oxidized, and so you and I will all just remember to put this minus sign in the formula that's in the data booklet. So I'm not going to think hard thoughts about should I flip this one, should I not flip this one. You just use this formula, and the 2 examples I gave you, first copper and zinc, I looked up the value for copper, I looked up the value for zinc, and I said the distance in between my figures was 1.10 volts. Karthika told me if I chose a more active metal than zinc, I'm going to leave the copper alone, but we changed this to be magnesium, and we got a bigger battery. It worked kind of exactly the way I thought it should. What kind of batteries do we use in computadoras? Lithium. Why do you think you use lithium based on table 25 or table 24? It's at the top. Oh my God, it makes so much sense. I mean, it's so pleasing. Like, some of this is really just pleasing. Like, I'd use lithium too if I understood how to do the chemistry, but if you expose lithium to water, you make boom. And so, like, I don't know how they do it. It's a dry cell, right? For a good reason. They tell me not to cut open batteries, and I'm thinking maybe they know what they're talking about. I think maybe, you know, air could do some bad things to them.
Doesn't Keisha kind of
I mean, everyone's cut open a battery once or twice in their life, but I'm saying, like, maybe there's some reasoning for not cutting open your batteries.
That's why they're warning
Don't care. Do you think you can actually do the homework based on this lackluster day? The homework was the other sheet of paper I gave you. Yeah, I did the homework, but I knew the answers before I came to class. Oh, I totally think you can do this. Damn, you can do this. So I'm gonna tell you one more thing. So if you guys are gonna put up with my altitude analogy for the cell potentials, like its gravitational potential, what do you notice is the definition of sea level? Hydrogen ions are the definition of sea level. Hydrogen ions define 0 on this chart. If you guys become high-powered biologists, you might not use the hydrogen definition of 0. They use something known as calomel. It's a mercury salt. Often it's their definition of 0. It's okay. It doesn't change anything but what 0 is. But the problem is that the hydrogen electrode is really hard to imagine. So if we have an electrode, we're looking for some sort of redox reaction to be occurring. And so the reaction that we have in mind for hydrogen, written as a reduction, because I promised you I'd do you that service, is going to be that. Correct? How do best? Yeah. How do I put that into a battery? Like, I understood how to do copper and zinc because I had copper and zinc. I could use like a little alligator or crocodile clip, depending on where you're from, to like connect some things. But here, I don't know what the electrode's going to be. I don't know how the electrons are going to be flowing into that other cell. And so we have to use an inert electrode. We're going to take one of those metals that never oxidizes and never does anything. Our favorite is platinum. Our reality is often graphite. And we're going to put platinum into the solution. We know that the platinum ain't doing nothing. It is just a way for electrons to flow out of this cell into the other one. We are going to bathe this in a solution of H+ ions. And we are going to shower this in an environment of hydrogen gas. I've tried to be really responsible with my circles. The circle means standard. And the standard state for all of these things is gonna tell you that the concentration of H plus is 1 molar. The pressure of a gas is 100 kilopascals, and any solids are gonna be pure. Just like you had to memorize what tetramethylsilane is for NMR spectroscopy, HL needs to be able to draw a SHE, a standard hydrogen electrode. You need to know that there is an inert electrode made out of something nice like platinum, and you need to know the concentration of the H plus is 1 molar, the pressure of the H2 is 100 kilopascals. This is our definition of standard, but this is an awful standard in a lot of ways. This is hard to make. We don't have one of these in our lab. It'd be a whole lot easier to make zinc the standard, right? I've got plates of zinc.
What is the whole point of
I do not know why they chose this as the standard.
but like, why do we make
I have 2 possible answers, and we'll see if either one is the right one for you, Audrey. Number 1, just like when we're talking about the altitude that you're at right now, I have to have some definition of what sea level is. And so this is the arbitrary choice of where the 0 is. So we're only talking about how far the electrons are falling. We don't really know where the electrons are. We're not measuring their true potential energy. So that's my first answer, clearly not the right one. My second answer is that we as chemists are profoundly interested in the pH of things, right? And it is possible to set up what's known as a concentration cell. So I can have something known here, and I can have something at a concentration I don't know here, and I can actually determine its concentration by measuring its voltage. And so this cell could be used to deduce the concentration of H+, and so has been a valuable means of determining the pH of a solution without using pH paper. So my understanding as to why we like this one so much is because it's related to finding the pH of a solution. Second one more close to the answer you wanted? Okay, I'm glad it was such a shit class. Good luck with your homework and enjoy going wherever you're going. I'm here to help and give you Pocky. Happy Pocky Day,